In this lesson, we're going to do an overview of the basics of rational functions. We're going to start by determining the domain of the rational function, look at its asymptotes, both vertical and horizontal, and then identify these three things based on the graph. So first off, what is a rational function? A rational function is the ratio of two polynomial functions. So if you don't remember, a polynomial function is a function that has expressions that involve only non-negative integer powers of x. So that means, something like a quadratic, a cubic, a quartic. Those are polynomials. So nothing to say the 1/2 power like a square root, that's not a polynomial. Nothing with absolute value symbols. Those are all examples of functions that are not polynomials. With a rational function, the domain is the set of all input values for which the denominator is not equal to 0. Because we know that really the only restriction on something that is made up of a fraction is when the denominator is 0, since we can't divide by 0. So let's find the domain of these two functions here. The function to the left is 6 over x minus 3. So in order to find the domain, what we really need to find is what values make that function undefined, because then we can exclude them from our domain when we write it in interval notation. So I'm going to start by taking that denominator, setting it equal to 0, and then solving that. So x minus 3 equals 0, which gives me x is equal to 3. That means that x cannot equal 3. So my domain runs from negative infinity to 3, and then there's kind of like a hole in the graph, so we're going to kind of skip over that 3. And I have a second interval with the rest of the domain, which is 3 to infinity. Now, this symbol in between these two intervals is just called a union symbol. All it does is join multiple intervals together. So if I have 5 intervals in my domain, I'm going to need 4 different union symbols. The function to the right is 3x minus 7 over x squared minus 4. So I'm going to do the same thing. I'm going to find where is that function undefined and then use that information to write my domain. I set x squared minus 4 equal to 0. We could solve this two ways. One way is using the square root property, which you see on your screen. The other way, I could have factored this. It's a difference of two squares, x plus 2x minus 2, and then use the zero product rule in order to solve it. Either way is correct, whichever is easier for you to remember. Solving it using the square root property, I moved the 4 over so that I could take the square root of both sides. Remember that when you're solving an equation using the square root property, that we do have two possible solutions. We have a positive value and a negative value. So x is equal to plus and minus 2. So that means that I have two values that are not in my domain, two values that make that function undefined. So when I'm going to write out my domain, I'm going to have 3 intervals. I have the interval from negative infinity to negative 2. Then I have the interval in between negative 2 and 2. And then the last interval is from 2 to infinity. Now, if that is confusing, you're not alone. It's not the easiest thing to visualize. What I always do is I try to think of it like a number line. So when I'm trying to find the domain in interval notation, and I have a bunch of values for which my function is undefined, meaning that those values are not in my domain, visually I think of it like a number line. So the first thing I do is I draw my number line and I mark off the values that are undefined. So in this case, we have negative 2 and positive 2. Then I kind of look at my number line from left to right and I say, what interval of numbers is in my domain? So when I look at the number line, I always start off at negative infinity, as you could see, and my first stop is at negative 2. That's my first interval. I'm going to skip over the negative 2, which is why we use these rounded parentheses, because the negative 2 is not included in my interval, and the union symbol. What's the second interval that is included in my domain? Well, that's everything that's here between negative 2 and positive 2. Again, skip over. We're not including the 2. We're going to skip over that. Lastly, I have one last interval that's from 2 to positive infinity, so it may even be worthwhile to mark your negative and positive infinities on your number line, and that's from 2 to infinity. So just something visual. If you haven't used interval notation, you should go back and watch my interval notation video. If you need help finding it, just let me know. But this is generally how you're going to write your domains. The next topic that we're going to talk about in this lesson is asymptotes. So asymptotes are just boundary lines that the function approaches, but it doesn't cross. And these lines can be vertical, horizontal, or oblique, meaning that they're slanted. In this particular lesson, we're going to stick just to vertical and horizontal asymptotes for rational functions. So a vertical asymptote can occur at any value for which f of x is undefined. So what's nice about this is that we already know where f of x is not defined. We know that it's undefined at certain points within the domain. If I already know the domain for f of x equals 6 over x minus 3, and that it's undefined at x equal to 3, that means there's a vertical asymptote there. So my vertical asymptote is the line, the vertical line, x equals 3. Something to note is that asymptotes are lines, so they must be written as equations of lines. Vertical lines are always of the form x equals a number. For that second example, we found that there were 2 values for which were not defined of this function, and that was positive and negative 2. So I have 2 vertical asymptotes in this case. I have one at x equals negative 2, and the second at x equals positive 2. So if you go back to my number line, at negative 2 and positive 2, there are actually 2 vertical asymptotes here. The second type of asymptote that we're going to look at is the horizontal asymptote. And really what the horizontal asymptote represents is a horizontal line that's going to represent that end run behavior of a rational function. Meaning, where is my rational function headed if my x values are getting really, really small or really, really large? Meaning, when I'm going towards both ends of infinity, where is the function, where are the y values going? So to determine the equation of the horizontal asymptote, I need to have information about the degree of the numerator and denominator. So if the degree of the numerator is smaller than the degree of the denominator, there will always be an asymptote at y equals 0. If the degree of the numerator is greater than the degree of the denominator, that's even easier. There's no horizontal asymptote that's going to be there. However, if the degrees are equal, the asymptote is the ratio of the leading coefficients of my numerator and denominator. So I'm going to go back to that first example. I have 6 over x minus 3 is my first function. The degree of the numerator here is 0. It's a constant. The degree of the denominator is 1. It's a linear function. So the degree of the numerator is smaller than the degree of the denominator. So that means I have a horizontal asymptote at y equals 0. In the second example here to the right, I have 5x cubed over x squared minus 1. The degree of the numerator here is cubic, it's 3. The degree of the denominator is quadratic, it's 2. So the degree of the numerator is bigger than the degree of the denominator, which means that there is no horizontal asymptote. This last example, we have a cubic on top of another cubic, so degree 3 on top of degree 3. That means that my horizontal asymptote is the ratio of the leading coefficients. Well, ratio just means I'm dividing them. It's a fraction. My leading coefficient here is 5. My leading coefficient down here is negative 3. So my horizontal asymptote is the line y equals negative 5/3. The last thing that I want to look at is, what does this mean graphically? What are these asymptotes going to show me? What is this domain? How is it going to look? So I'm going to go back to that first example because there's a lot of information there. I have 6 over x minus 3. I know my domain is from negative infinity to 3 and 3 to infinity. So I'm going to have an asymptote, a vertical asymptote, at x equals 3. So we could see that right off the bat, our function is split into two because of that vertical asymptote. If I had two asymptotes, I would have three pieces of this graph. The more asymptotes, the more the graph can be broken up. My horizontal asymptote here is the x-axis, it's y equals 0. So notice how as x is getting smaller, this half of my graph is getting closer to the x-axis, it's getting closer to 0. As x is getting bigger, we could see the same thing is happening. This half of my graph is getting closer to 0. Also notice how when I get closer to this value x equals 3, each half of my graph is also getting closer. So the asymptotes we get arbitrarily closer to these asymptote values, but we generally don't cross over them.